All right.
So, Danny, everybody, Danny.
Okay, so I'm very, very excited to be talking in this beautiful weather. So let's get started. So I'm going to now explain how what we just saw in the previous talk is a low-dimensional manifestation of a much more general theory that I won't define in, I won't explain to the greatest extent that this can be defined. I mean, maybe at the end I'll say something about SFT, but more likely I'll run out of time. So what we're going to try to do is to define some version of this Legendrian contact homology for a contact manifold that is of this form. So P is going to be an exact symplectic manifold with Liouville form theta, and then the contact structure on this product, which is called a contactization, is going to be given by the kernel of this form. Okay, so this is a contact form, and
Z is the direction of R.
so Z is the direction of on R, and moreover I will think of it as the same Z as we had before. So in our previous case we had P is equal to R2, and then this is the Z coordinate, and then I have to assume a couple other things. So necessarily, because the manifold is exact, it's going to be non-compact, and if I want to have some sort of control on holomorphic curves, I need to put some conditions on the geometry of this manifold at infinity. So we're going to assume that P has finite geometry at infinity, and this is some technical condition that ensures that holomorphic curves cannot escape to infinity. It was introduced by Gromov. I'm not going to get into the details enough that it's going to matter what this is. So if you're not familiar with the notion, let's just assume that P is convex at infinity. So maybe it's a Liouville manifold or a Stein manifold, and if you just want to be even more explicit, let's just make this the cotangent bundle of your favored manifold V. And so in this case, P cross R is the one jet space of B with the usual contact form. And if you take even more concrete, if you take B to be Rn, then P is just Cn. And this guy is R2n plus 1. So for the purposes of the talk, you can assume that is the case. And then I will also assume, so recall that the bundle of almost complex structures that are compatible with omega, which is almost complex structures J that are omega compatible. And what this means is that this defines, so here omega is d theta. This means that this defines a Riemannian metric. This bundle has non-anticontractable fibers. And so I have a well-defined first Chern class of this of the tangent bundle to P with respect to any of these complex structures, and I will assume that this is zero. I will make comments of how you can salvage the situation if it's non-zero, but let's assume this to be the case, as it will be, for instance, if we're working in Euclidean space. Okay, so this is our manifold, and then I'm going to consider a Legendrian here. And again, you can try and make things a little bit more general, but let's assume for this talk that it's connected to compact. And I'm going to define pi to be the projection onto P, which you should think of as the analog of the Lagrangian projection we were seeing before. And I'm going to assume that pi restricts to L to an immersion with transverse double points. Which just means that the pictures look like they did before. If this was your unknot, then the projection is going to look something like this. And so the double point, if I concentrate on the double point, it's just nice. It has a nice local model. And I will just say this in words, but in general you want to also take your complex structure so that it's integrable in the neighborhood of the double points, and so that in fact these two branches are real analytic. This is technical. You actually need this to make the proof work as they do it, but I will shove this under the grass for the purposes of this talk. Okay? So that's so far. And then, so for such a setup, the set of Rabe chords.
Do you consider the case when we have infinite number of double points, or just always?
Well, if L is compact and it has transverse double points, it needs to be finite. Yeah, I mean, I'll get there. So the Rabe chords are trajectories of the Rabe vector field, R is ddz, that start and end on your Lagrangian. A comment, by the way. You could be like, well, why are you talking about contact manifolds of this form? It's like, what's up? And the thing is, so again, there's something a little bit more general you can do, but if you have periodic Rabe orbits, the algebraic structure is more involved. The LCH is a module over the contact homology, and you cannot define things with geometric perturbation methods like we're going to do here, and so at the very least you need to assume that your contact manifold has no periodic Rabe orbits. Here I'm assuming a little bit more, which is I'm assuming that the set of Rabe orbits is a manifold, P. I'm quotienting out by the Rabe flow. And so this is sort of somehow a little bit more than the necessary assumption that there's no periodic Rabe orbits. Okay. So the comment. So these are the Rabe chords, and then my contact homology algebra is going to be the free algebra over this coefficient ring generated by the Rabe chords. Free associative algebra. I was convinced by Roman to do things in a greater level of generality than the bare minimum. So I'm actually going to give the definition with these coefficients, but you can set all of these variables to be 1, and then you get a theory over z, and then you can reduce mod 2, and then you get a theory over z mod 2 in which you don't have any orientations. And there's different things that change with the different choices, but we're going to try and set things up this way. And I will make the comment that indeed we only have finitely many Rabe chords. Okay, so there's various possibilities for the grading, and with the assumption that this Chern class is 0, this algebra is graded over Z. In general, it might be, so it's graded over Z, assuming I'm going to make yet one more assumption, that the first homology of P is free. And if you don't have this condition and this condition, you might be able to grade it over Z mod the minimal 2 times the minimal Chern number. If this isn't free, it's kind of harder. You always have a Z mod 2 grading, and I think you can also define a relative grading over a cyclic group, maybe Z mod the rotation number, but in this case it's not really clear what the rotation number of the Legendrian is. I'm going to just keep assuming this condition from this condition and define a grading over Z.
Sorry, but this problem doesn't go away if you put the H1 variables to 1, or does it, with the non-free H1? So does it persist on the...
It's H1.
No.
Yeah, this is not, this L and P are different.
Graded over Z mod 2.
Yeah, okay.
And let me just quickly say a word about how to do that. So you fix a basis of H1. It's going to be some sort of Maslov index, but we just have to pick some bases, and so there are some choices involved. So you pick, let's see, and each of these guys I'm going to consider as represented by some embedded loop. So this is actually an embedded loop. And now for every rate chord C, I'm going to choose a capping path, which is a path in L joining the endpoints of C. And I'm going to choose, even further, a surface sigma sub C, which realizes a homology between, on the one hand, the union of this capping path and the chord, which is some fixed loop. Okay. So in the previous, so the example, let's see. So here I have a rate chord C, and a capping path is, for instance, let me just use a color, and then I could choose a capping path here. In the case that we were doing before, things are explicit enough that we can make a consistent choice of capping paths, but in general, there's no reason to choose one over another, and there's various components in the space of paths joining these endpoints, so you have to pick one. But once you have one, this is some class in H1 that is homologous to some combination of these. So I'm going to be sloppy, but just bear with me. So it's going to realize a homology between, let me just, maybe with signs, the surface is going to realize a homology between this loop and some combination of the generators. Okay. More choices. I have to, well, it's not really choice, so I have a fixed trivialization of TP, the tangent space restricted to each of these. Okay. Now you can check that this induces the trivialization of TP restricted to my loop. So there's a unique way to extend the trivialization that I have of the tangent bundle over this end of sigma C to the whole of sigma C, and this gives me a trivialization of the tangent space over the capping path union the rate chord. And so I can think of the tangent space to L along delta C as a path of Lagrangian linear subspaces of Cn with respect to that given trivialization. And now I can close this path up in the standard way to get a loop, and the Maslov class of that loop is going to be my grading, essentially. So the grading of C is going to be the Conley-Zander index of that path minus 1. Okay, I can say more about this if people want me to. Do people want me to?
Maybe it's useful in the, I don't know, I like this formula very much in the jet space when you have it's explicit in the same vein as the rotation number that Marco represented like, then it's like the Morse index of the front projection minus down, plus downwards, minus upwards, minus 1 or something like that. This, I don't know, for some reason
It's going to depend on the capping path, though.
No, I mean, for the capping, that's the so you choose a capping path, you have some downward cusps, you have some upward cusps, plus downwards, minus upwards, and minus 1. It's very neat.
Okay,
don't
yeah,
write.
I mean, you can. This is a rotation number, and if indeed your path goes through simple singularities that are rotating, then you can compute this combinatorial.
Very neat formulas, that's great.
Okay, so there's combinatorial formulas for this. But yeah. I mean, okay. What is the Grassmannian the Grassmannian of Lagrangian linear subspaces? Maybe I can say this is UN mod ON. You have the determinant, which is a map from UN to S1, and the determinant squared goes down to the quotient, and so you can use the determinant squared to pull back the fundamental class of S1, and then that gives you a one cohomology class, and you pair that with a loop, and that gives you a number. That's the Conley-Zander index. And so this is, yeah, and the grading of a homology class is going to be minus the mass law for A H1. Mu being this
H1 of P.
what's that?
Is it H1 of L or P?
Of L. So I need to define a grading on these generators, but the coefficient ring is also graded, and I'm saying that a class A is graded in that way. So again, you take a class A, you represent it by a loop in L. With respect to those choices, you can think of the tangent space to L along that loop as a loop of Lagrangian subspaces, and then you take minus the Maslov index of that loop of Lagrangian subspaces. Any questions?
Is the genus of the surface sigma c matters?
No.
But there's a choice for the sigma c.
Okay, so there's a choice, but different choices will differ by the union of the two surfaces, and that's a two homology class, and they will differ by how that second homology class pairs with the Chern class, which is 0. So it doesn't matter if there's a choice. If the Chern class is not 0, then it will differ by a multiple of the minimal Chern class, and then you have a grading over Z mod, actually twice that number because of this too. Yeah. Any other questions? So yeah, I mean, I don't expect like this to be rememberable after I erase it, but I just wanted to give the grading, the full grading definition.
Excuse me?
Yeah.
This is a computation of the Conley-Zander. Do you have, for example, an example for G1 or S1 or something? You know where the homology class appear because.
So what is the question? How to close up a path?
I understand the Conley-Zander in the case where P has no topology.
Yeah.
Rn, but when there is some homology class, I'm not too sure.
Yeah, so this is why you are fixing a trivialization of this tangent bundle over the basis of H1, and then you're computing it with respect to that trivialization.
Okay.
So
I was asking for an example, just if you have one.
J1, S1.
For J1 of S1, there's sort of an obvious trivialization, and everything works exactly as for J1 of R. Yes.
Yeah, okay. So yeah,
Yeah.
you don't have to choose.
You don't really have to choose it.
Yeah, okay. Okay, so maybe it would be too complicated an example.
yeah, I mean, I'm not particularly sure it'll be so instructive, but
Okay,
But you could take this example and just twist the utilization, choose a non-natural one, and then you screw up everything you're used to. But you can do that. You can choose a different orientation from J1 as well.
Okay, so now I want to talk about moduli spaces. Oh, maybe I should say something about dependence on choices. So I had said that indeed it doesn't depend on the surface that you choose, because the first Chern class was 0. It does depend on the capping paths, but if I choose different capping paths, I will get isomorphic algebras, and the isomorphism will be given by a homomorphism of the base ring Z bracket H1 of L. So this is independent of choices if you say things the right way. Okay. Moduli spaces. Okay, so I want to define some moduli spaces. So let D m plus 1 be the unit 2 disk with m plus 1 boundary punctures. So it's this guy, and then I take away a P0, P1, ... Pn. And now let M A cross AB for a raid chord be an ordered tuple of raid chords. Won't write it. And A homology class in L be the space of maps U from this punctured disk to P such that the following properties are satisfied. Okay, let me maybe fix an almost complex structure first. So J is an almost complex structure that is compatible with a symplectic form, and so I'm going to want U is holomorphic in the interior of the disk. U is continuous. All of the disk. U maps the first boundary puncture to the Lagrangian projection of A, which is just a point. Positively, I will say something about this in just a moment. And U Pj times Bj negatively. And U restricted to the boundary of this guy, so minus the Pj's, lifts continuously to L. So what do I mean by positively or negatively? Well, so we have a well-defined z coordinate, and there's going to be 2 branches above any raid chord. Okay, but if I have a holomorphic disk, so maybe this is U, the image of U. It comes with an orientation, so there's a I can define I can think of an orientation in a 2-dimensional guy as a counterclockwise or clockwise specification, and so positively will mean that I'm kind of going into the lower point and following the rate chord and then leaving, and it'll be negatively if the opposite things happen. So punctures can be positive or negative, depending on whether I go up or down. Is it clear? Okay, so this is your moduli space, and
So nowhere in there did you say it was J holomorphic, right?
yeah, I said it's holomorphic in the interior.
Oh, there it is. Sorry, I just can't read.
Sorry, it was badly written. It's also abbreviated without warning. So those are your moduli spaces, and then the 2 main properties that we're going to have is that they are they can be transversely cut out by a generic choice of either J or L, and they are compact in a suitable Gromov sense. So let me also define. So let me talk about compactness first. and let me say what a broken curve is.
Sorry, before you move on,
Sure.
how does A play into this?
Sorry?
How does A?
So so I have m plus 1 punctures. Oh, thank you. The A capital. Yeah,
Yeah.
great. So, what I'm going to ask is that the union of B. Okay, so the union of the rate chords that I end up with together with their capping paths is in homology class A. Thank you. Okay. So yeah, so my holomorphic curve, which is a polygon. I mean, I'm not even going to draw a picture because it's the same picture that was drawn in the previous talk. It's some holomorphic polygon, and now if I get, yeah, sorry, no, this is. That's not what I want to say. Sorry. The chords are not in L. The chords are not in L. Right? What I want to say is that U of the boundary of the disk union the capping paths is A. I think that's what I want to say. Yeah, the other thing was just nonsense. So
Johnny,
ignore it.
I'm a bit confused about this diagrammatic picture that you have
Yeah.
about positively and negatively. 'Cause
Yeah.
U is just happening in P, so like you don't see the actual wave direction.
Well, I mean, of course they lift, but you can still specify. So you still have, so in the source, you still have an orientation induced on the boundary. And so it could either be that this is on the lower branch or this is
I
in the
see.
upper branch. If this is in the lower branch, it's positive. If this is in the upper branch, it's negative.
Great.
And sorry, okay, so the image of the boundary is not a closed curve in L, because if I try to lift it in L, I have these gaps. Fortunately, I've chosen some capping path, delta C, and so as Kevin pointed out, this isn't really here. And now if I take the union of what U is doing in the boundary with my specified capping paths, then I get a homology class, and I want that homology class to be A.
But that's still the union over all J, right?
Yeah.
So that A.
Okay. More questions? Yeah.
So I just wanted to comment that you can do this where the homology coefficients don't commute with wave chords, right? And then each section of the boundary of the disk gives you some homology class. That may be useful for later on in the week.
Okay. More questions or comments?
Sorry, what was the comment again? Oh, that you can do this where the homology classes do not set up the algebra where the homology classes don't commute with wave chords. And then each component of the boundary of the disk gives you an element in H1 of the Legendrian, and so you sort of have an alternating product of wave chords and elements of H1, and d squared will still be 0, etc.
How each segment give the homology class depends on some code.
Oh yes, you have to choose. So in addition to these capping paths, maybe you have to actually have them go through a fixed base point, and then you have so that you split each capping path into two. So each endpoint of a wave chord gets connected to the base point, and then if you concatenate them, then you actually get closed loops in the Legendrian.
Okay, so I'm not going to define what a broken curve is because you can imagine it. So it just means it's a bunch of these curves that I just defined that match up and form a tree. So each of these i's is going to have exactly one positive puncture, and then a whole bunch of negative punctures, and then maybe at some of these negative punctures I have some other disk that has a positive puncture matching up with the the negative puncture of the previous one in the image. Maybe this is U2. Negative, negative, negative. And maybe this one branches further on, and maybe this one also does. And what I want is that the quotient space obtained by identifying these is a tree. And so this is a broken curve. Yeah, absolutely. Okay, so what is Gromov compactness? In this case, it says that every sequence of curves converges to one of these. So let me just write that. So theorem, every sequence UN in one of these fixed guys converges to a broken curve. And moreover, with the obvious notation, I have that this expression, which will come up in a moment, is equal to this expression, and homology class breaks up. So.
Is this why you want no periodic orbits?
So, yes, amongst other reasons. So let me say a word about the proof of that. So what kind of things could happen? So Gromov compactness is the thing, and so what could prevent what other forms of convergence could we have? Okay, so the curves could escape to infinity. We've forbidden them by putting some technical condition at infinity, which is either convexity or finite geometry or whatever. Okay, so they stay in a compact part. Now, they could develop bubbles. They can't. P is exact. They could develop disk bubbles. They can't. P is exact and L is an exact Lagrangian immersion because it came from a so no bubbling. And then you could have indeed part of a curve converging to a periodic Grabe orbit. That could also happen, but we have no periodic orbits. So this is the only possible degeneration that could happen. That's proof. So that's compactness, and then we have, okay. So any questions about compactness? I know that wasn't very thorough. But. Okay. So now we have regularity, which is that. Okay, I'm going to be a little sloppy here, but generically, M A B is a manifold of dimension given by this index minus 1. So this is regularity. So a word about regularity. So if I had, so the reason why Legendrian contact homology is something that can be well defined without using virtual techniques is that there's no periodic orbits and there's no multiply covered stuff. This is here all of the, so in general, how do you prove regularity? Well, you consider the Cauchy-Riemann operator, and then by elliptic theory you know that it's Fredholm. So to show that this is a manifold, being the zero set of a Fredholm operator, you just need to show that this Fredholm operator is surjective, or can be made surjective by generic choice of the data. Now, if you have multiply covered stuff, and it's impossible to do this because you do not have an equivariant Sart's theorem. Sorry. In this case, so one usual way where one does this is one finds some injective point on your holomorphic curve, and then one perturbs your complex structure near that injective point, and that gives you transversality. Here you need not have an injective point, but the key point is that you only have one positive puncture. And so you can actually deform things near that one positive puncture to obtain that transversality. So this one positive puncture plays the role of an injective point. Maybe that's all that I'll say. What about the dimension? Well, by the Riemann-Roch theorem, you know that the index of a Fredholm operator can be computed in terms of some topological index, and that involves some Chern class, and the Maslov index is essentially a relative Chern class.
But you can't say that there are injective points near that positive. You cannot.
No. I mean, I have not looked at the proof in a lot of detail, but they very clearly say there need not be an injective point in such a curve. However, the fact that you only have one positive puncture still allows you to do the perturbation in such a way that the negative punctures don't, other stuff coming from elsewhere doesn't affect what's happening there. Okay, and now I'm going to say one more thing, and moreover, if L is spin with a spin structure fixed, and if you choose so-called capping operators for each of the rate chords, then this moduli space is naturally oriented. So I will not say anything else about this, but this is some coherent orientation scheme that you can do, and in general, if L is not spin, this is just false. You cannot coherently orient these in such a way that you'll end up with a nice algebraic structure. But if L is spin, then you can make some choices. This orientation depends on those choices, and we will later see how the theory depends on those choices, or doesn't. Questions or comments about these moduli spaces? So something that I forgot to say, that was on my notes, is a basic thing that you need for Gromov compactness is some uniform bound on the energy. And I didn't tell you why you have that. And so you have that because the difference in the z coordinates between A and the B's by Stokes' formula is the integral on the disk of the pullback of the symplectic form by the map, and this is the holomorphic area of U, also known as the energy, and so you actually have a uniform bound on the area just based on the action difference. And so that gives you the uniform bound on the energy that allows you to go through with the Gromov compactness argument. This identity will be useful later on, so I wanted to put it down there. Okay, so the differential. Okay, any questions? So let's define a differential from our algebra to itself in the following way. The differential of A is going to be the sum of over all moduli spaces of the form just described, which have dimension 0, and there's some terrible sign here which I will never remember if I don't check. And then the number of points of that moduli space counted with the signs given by that theorem, and relative to those choices, times the class A times B. So if I have a tuple of rate chords, what is the coefficient that that tuple comes with, in this differential, it is the sign count of rigid holomorphic disks with one positive puncture at A and the negative punctures in that order being your given tuple. And then with some weird sign that comes from some gluing of rigid disks. Like, just don't ask me about that.
So sorry, 2n is the dimension of P?
Yes. Okay, that's the differential. And now, theorem, del squared is equal to 0. And because of the assumptions that we've made, this is pretty automatic. So this is the same. Recall what you do in Morse theory. And so if you put a Morse complex, how do you show that del squared is equal to 0? Well, you identify the space of broken trajectories with the boundary of a one-dimensional moduli space, and one-dimensional manifolds have an even number of boundary components, which is even 0 if you count them with sign, and so the contributions cancel in pairs, and this is a little bit the same. So d squared counts broken curves u1, u2, and you show that these are precisely the boundary of a one-dimensional moduli space curves of index 1, 2. And this is where your algebraic structure just goes completely bananas if you have periodic orbits, because you will have other contributions that you're not, I mean, it just won't be true that d squared is equal to 0. You will have some sort of algebraic structure, you will have some module structure over the contact homology, just d squared will not be 0, so sorry. But if you are in the setting that we're describing, then the only possible degenerations are into these broken curves, and so you're good, and d squared is 0. Okay, and then what is the Legendrian contact homology of L? Well, it's the kernel delta, but modulo the unit. Okay, any questions? So, so this is your guy, and now maybe I'll make a remark. Okay, so I want to make a remark about the previous lecture, but I'll pause for questions. Okay. So suppose that P is equal to R2. Okay, observe that if a disk has a branched, okay, so observe that branched points can move around. That is just, okay, so if I have some map of the disk to R2 that is holomorphic and has a branched point, then it will never be rigid, because I can move that branched point around. What does that mean? That in this expression, in R2, the only disks that contribute are immersed holomorphic disks, and by the Riemann mapping theorem, I can just count regions of the plane, and so you get the combinatorial description that we had in the previous lecture. So this reduces, if you are careful with signs, to what we knew before. Okay, so that's that. Okay, invariance. So this is great. You've defined this thing, but what is it an invariant of? So, so fun fact. LCH of L does not depend on spin structures, etc., over Z mod H1 of L, but it does over z. It's kind of crazy, but it's interesting, and you can just see very simple examples of with the unknot of why this is true. So over this coefficient ring, somehow these guys can take into account the difference given by the spin structures. But so if we work on this theory, this is actually, you have to make some choice of coherent orientations, but they don't change the answer. This is a little bit like in Morse theory. When you set up the Morse complex to orient things, you have to arbitrarily choose orientations of the negative eigenspaces. But then once you've made those choices, you get some homology over z, which is independent of those choices. So this is the analogous fact here. And okay, but then there's some other things.
Sorry, is there a universal coefficient sequence from
I
the
do
big
not
ring
know.
to the small ring?
I do not know the answer.
Sorry, what was the question?
If there's a universal coefficient sequence from the big ring to the small ring.
Yeah, I don't know.
Okay, so theorem, LCH of L does not change, and I will be more precise about this in a moment, does not change under Legendrian isotopy of L or homotopy of J. So it turns out that it's an invariant of L. So we're going to see something a little bit stronger in a second about the stable tame type, but I just wanted to point out that this simpler theorem can be proved using the standard approach from Morse theory. For every homotopy, you define a map by counting index 0 curves. Then by counting handle slides, you show that this map is then you show that this map is actually a chain map, and then you show that this chain map actually didn't depend on the homotopy. And in every case, what you do is you study the boundary of some moduli space of curves. So this is actually not so bad. You can do it with the same Morse theory because you have no periodic orbits, and so it's just the simplest Flora theoretic setup. So this is not so bad, but actually a lot more is true, which is that the stable tame type of the DGA A delta is also an invariant. So this is something stronger. And I want to say a word about why that's true. So what time did I start?
15 or 20, I don't know.
11:15?
Yeah.
So am I like out of time?
No.
No?
Still have 5 minutes.
Oh, great. Okay,
Maybe.
then,
Maybe even 10.
well, then I probably should say something about augmentations. Let me just say very quick word then about why this is true.
How much
So-
are you willing to pay for 5 more minutes?
5 more minutes?
Yeah.
I mean, up to you. Like, I would take probably a few more days if I could. But.
Yeah.
Okay, fine. Then let me just say a word about this. So first, suppose that L moves, but I have no new rape chords created. No rape chords are born or die. Then consider the moduli space which consists of the pairs UT, so JT, LT. I will deform both at the same time, I don't care. Such that U is a curve in this moduli space, but for the data defined at time t. Okay. So generically, and I'm going to assume that, that the expected dimension of this moduli space is -1. So let me just write this in full. Okay, so the expected dimension of each of these individually for each individual t is going to be -1. But because I have a one parameter family of them, for isolated times, I will expect to see curves appearing here. And each of those curves will be a handle slide. And each of those handle slides will modify the differential. And how do they modify the differential? Well, you can see that what will happen is that dA will move to be dA plus or minus a times the differential of b. This will happen as you pass through a time tj such that this moduli space tj is non-empty. Okay, and so what it means is that if you do the calculation, is that the homomorphism that sends a to a plus or minus ab and sends all other chords to c is an isomorphism of DGAs, and by the definition that we had, it's actually a tame isomorphism of DGAs. Okay.
What is capital A here?
It's the homology class.
It's the same one as above?
Yeah.
So that depends on, I mean, you want this to work for all, I'm a little bit confused about what's going on here.
So, yeah.
The differential sums over all possible homology classes.
Yeah.
Right?
I'm just, fine. Yeah, but so you can set this up so that for each individual time there's only a change in one of these moduli spaces, and at that individual time there's only one change to the differential, and the only change is by a term like this.
Great.
Okay, and let me just do you the proof in Morse theory. So
It shouldn't be dB. Should it be just b maybe?
AB. No, the differential. You'll see what it is. So suppose that this is A and this is B, and they have the same index. So this ascending manifold and this descending manifold generically don't intersect. And now I'm about to handle slide. So these so when I handle slide, what happens? What happens is that this guy moves over, and sorry. What happens is that this guy moves over and eventually links together with this ascending manifold, and so in the end, what happens is that the descending manifolds give me the connect sum of A and B, and so you can see that to the differential of A, I now kind of add whatever homology class that had plus the differential of B. So as this handle slides over this one, I pick up precisely the contribution from the differential of B. Okay, I don't have time, I'm sorry. I would love to explain this more, but I just don't have time. And so I'm just going to say what happens when I create two new rate chords. So suppose that this is pi of L. So when I suddenly create two more intersection points, what I do is I construct these two generators. I have to add these two rate chords, and you can easily check that there is one rigid disk. And if you do some computation, you can actually show that nothing can escape a small ball, at least for small time. So this is indeed the only contribution. And so what you're doing is that you're passing from A to A direct sum this standard guy with DE2. So the motto is, as you pass through, as new rate chords are created, you are stabilizing, and as you pass handle slides, you evolve via a tame isomorphism. And so indeed, the stable tame type of the DGA is preserved. This you should compare with the Morse theory picture, where if I suddenly create two critical points, there is one unique trajectory from one to the other. So it's exactly the same as in Morse theory. Okay, so I just need to, so this is obviously out of the question, so let me just say a word about augmentations. So as was said, LCH is not computable. And so what did Chehanov do? Well, he realized that so first of all, divide the differential between parts that send, so this lands in products of I rave chords. And so if the zero part of the, let me put the index here. If the zero part of the differential is zero, then d1 squared is 0. And so you can use this linear differential, which sends words of length 1 to words of length 1, to define the linearized contact homology. And now this is something that is definable, and that is computable. And because it's not just some crazy DGA, it's just some vector space, finite dimensional vector space. In general, this need not be true. So what is the definition of an augmentation? An augmentation is going to be a DGA map from this guy to the reduced over Z mod 2. I'm just going to do this over Z mod 2. To the trivial DGA, and then if you have one of these, you can use it to twist delta, the differential, into some other guy, such that the 0 part is now 0. Okay, and so you can, given an augmentation, you can use it to linearize the Legendrian contact homology. And the invariant that Chekhanov actually defined is the set of Poincare polynomials of all linearizations of the Legendrian contact homology. And that was something great. And that's what he actually used to distinguish Legendrian knots with the same classical invariants. But now, what is a problem? That augmentations need not exist. And indeed, they often don't. Often, another question you can ask is, like, where do they arise? And okay, it turns out they come from geometry, they come from Lagrangian caps, and there's some nice interpretation of them in terms of counting. But you don't always have that. So that's just not good enough. And so what Lenny defined, which turned out to be very useful because it exists even when augmentations are not a thing, is called the characteristic algebra. And so what is the characteristic algebra? It is the quotient of A by the double-sided ideal generated by the image of the differential. Okay. And you should think of this as a universal augmentation in the sense that every augmentation epsilon factors through this stupid DGA. So it's not an augmentation in that sense, but it is every augmentation factors through it somehow, and it's computable, or it can be computed if you spend enough time, and moreover, there's this theorem. George's what's the surname? Roman, help me out. So that the LCH actually embeds here. What's that? Is that guy? What's your surname? What's that?
Dimitroglu.
Dimitroglu?
Yeah.
DR? I'll just point to him. Yeah. Okay, so this guy proved this. Is this correct, that the LCH embeds in the characteristic algebra? Yes. This is a monomorphism. And so in fact this is computable and has as much information as the LCH. So this is a great thing, and yeah, I have more to say, but I think I'll just stop here.
Questions, comments? Maybe I'll make one comment relating your talk to the talk of Marco. So you said that sometimes augmentations do not exist, and Marco mentioned the stabilization. Right? So whenever you have stabilized knot, this is a particular situation where augmentation doesn't exist. So you have an algebra and this algebra.
And the characteristic algebra can be non-trivial? So it vanishes with an augmentation. But then
So this thing that does not depend on spin?
yeah.
And I'm not really seeing how does that work, because I would think that if you go to H2 relative homology, then MIT doesn't depend, but couldn't you have some classes here?
So the differential changes,
Yeah.
but you can construct an isomorphism of DGAs, I believe, induced by a homomorphism of the base ring, which takes into account how the no, it might not be of the base ring. Okay, so I'm not remembering the details, but they have a very explicit formula for how the differential changes, and it's some pairing between the homology class in question and something that comes out of the spin structure, and then you can twist by that factor and relate the two DGAs. And the problem is over Z, you cannot twist by that factor because you do not have the homology.
But you sure that argument is not on relative H2 instead of H1 as well?
Well, I think it's basically just you change the signs of these H1 generators in the group.
Yeah, so just changing a spin structure is a class in H1 with H1 of L with Z2 coefficients, right? Did I get that right? Yeah. So any such class you can then get an automorphism of this base ring by either keeping each generator or negating it.
So you're saying that the spin structure might live in something like H2, but the change in spin rates is in relative H1
with Z2 coefficients. Just
the
regular
obstruction to spin is in H2.
The different spin structure.
Right.
So if you fix a spin structure, then relative to that spin structure, every other spin structure can be given by some element in H1.
So that's why it works. Okay.
Yeah.
Great.
So I actually have a question. So in this Chekhanov paper, it's said that you define these as the tame automorphisms, and as these elementary automorphisms, and then tame is something that is composition of elementary. And at the time of the paper, it was not known whether there are non-tame automorphisms. Is this still open?
I think it's still open.
Okay.
But I also think that nobody has thought very hard about it.
What's your feeling?
Sorry?
What's your feeling?
It seems like that probably all automorphisms are tame. I don't know. I don't have a strong feeling.
Does it matter?
In some sense, it doesn't really matter.
But maybe once you said it in the more general setting, then maybe DJ homotopy is more to the point, which is stable tame implies DJ inverted about the DJ homotopy. So it's more useful in practice.
Let's thank them again.
So, just one thing before lunch, we have to carry everything back in.